Thank you, Lavinia, and thank you also to the organizers for this really nice meeting. And also, especially thank you for pronouncing my name perfectly. So, I will be using in my talk a specific mechanism for suppressing Lorentz violations in the matter sector to motivate some extensions of Horava gravity. I will start with a kind of a review of Horava gravity, focusing on some of the fundamental properties, like how you do the power counting, how can you show that the theory is power counting renormalizable, and then show you how the construction goes on, and that will be useful in the last part of my talk. And in the second part, since Diego really talked about almost everything, most of these will be overlapping with what he said, so I will try to get some theoretical and observational constraints on the IR theory to determine what the types of Lorentz violating scales we can have. And then I will move on to show how difficult it is to violate Lorentz invariance in the matter sector based on the observational constraints. And then I will talk about this promising mechanism which relies on a scale hierarchy, which was introduced by Costello and Shang. And basically I will be focusing on this mechanism the rest of the talk. And there are some shortcomings of this mechanism which can in principle be fixed among maybe other possible ways. But one way to fix it is to add some mixed derivative terms. And although it was initially considered as some deformation of Horava theory, I will take it at face value and basically consider it as some fundamental property of the theory. I will calculate some propagators and then basically try to reformulate the whole counting arguments. So now, we know general relativity is not renormalizable as a perturbative quantum field theory, but we also know that if you add higher order terms in the curvature, like Stella did, you can have an improved UV behavior. You can get this nice k to the 4 behavior of the propagator in the UV. But this comes as a cost, with a cost, and that's basically you get a new degree of freedom, a massive ghost in this case. On the other hand, Horava's idea is basically to introduce some kind of anisotropy between time and space at high energies, such that you can have higher spatial derivatives and all the good things that come with it. The UV behavior becomes better. But also such that you don't have any more than 2 time derivatives, so that you don't break into it. And this comes with another cost, that's the violation of local Lorentz invariance. And usually people explain how the theory is power counting renormalizable based on some toy model of Lipschitz scalar. And here I'm going to specify to 3 plus 1, but this can easily be generalized to higher dimensions as well. So the scalar has 2 time derivatives and 2z spatial derivatives here. These gradient terms are here. And this basically requires a special scaling such that the coordinates, spatial coordinates, scale like an inverse of momentum, and the time scales as the inverse of momentum to the z. And if you look at this, you can calculate the dimensions of the momentum dimensions of the scalar, and you get something that depends on this power. And to put it into perspective, in the Lorentz invariant case, when you have z equals 1, you get the usual scalar field, which has momentum dimension 1. On the other hand, you can also see that if z equals 3, you get dimensionless scalar fields. And so if you move on to include some interactions that are non-derivative, then you can actually calculate the momentum dimension of the coupling constant, which is like this. So if this is positive, then you can have power counting renormalizability in this naive dimensional counting. And again, if we look at the relativistic case, you can see that this is 4 minus n, where n is the power here. So basically this tells you that up to 5 to the 4 theory is power counting renormalizable. But you can also notice that when z equals 3, this term vanishes, and you get something that is manifestly positive. And this also goes true for higher z. If z is higher than 3, this is again positive. So basically, this is the condition for power counting renormalizability in this Lifshitz scalar theory, which has non-derivative self-interactions. And you can do a more proper calculation of superficial degree of divergence with including derivative interactions, such that, I mean, this is a scalar field basically, but you're trying to mimic the way gravity is behaving. And you can actually add up to 2z derivative interactions. And you can find the qualitatively, but quantitatively as well, the same result. Z greater than or equal to 3 is power counting renormalized. So this is the case for a Lifshitz scalar. And then the idea is to somehow apply it to gravity. Of course, just having this anisotropic scaling is not enough to define the theory. You need to define, I mean, the way Horava did was to define basically a symmetry like this, where you have a time repermutization symmetry that is independent of coordinates, and 3D diffeos that are time dependent. This is the foliation preserving diffeomorphisms, and because they prefer the way the space-time is foliated, the ADM decomposition actually provides a natural parameterization. So you have this standard decomposition, where now your fundamental variables are the lapse, the shift, and the three-dimensional metric. For now, I'm keeping C to be arbitrary because now, in this case, because time and space have different dimensions, C is also dimensionful. So it has a dimension of momentum to the Z minus 1, and so does shift and lapse and metric have 0 dimension, and so on. And then you can start writing down the kinetic terms and the gradient terms. So first of all, the only way you can write down the time derivative of the metric in a covariant way, I mean, the only quantity that transforms covariantly, which includes the time derivative of the metric, is the extrinsic curvature. Covariant in the sense of this symmetry. And if you look at the dimensions, it also has momentum dimension Z, just like in our Lifshitz scalar analogy. So we can basically, these count as one time derivative. And the symmetry allows only 2 terms for the kinetic part of the action, which is basically Kij squared and trace of K squared. And because we're adding only up to 2Z dimensional operators, these are the only terms that we can write. So now we can move on to the gradient terms. So for gradient terms, the building blocks that we can use are, first of all, the 3-dimensional curvature invariance. So you can have the 3-dimensional covariant derivative, which has 1 dimension, and the curvature tensor has momentum to 2. And there's another building block that basically is the acceleration vector, which transforms like a vector under the 3D transformations. And this has dimension 1. And now the plan is basically to write up to, well, I will be considering 3-dimension, 3 plus 1, with the minimum case, which seems to be power counting renormalizable. That means I will include up to 6 spatial derivatives. And the building blocks are the acceleration vector, the curvature tensor, and the covariant derivative. So you can write many terms using these. There are some simplifying assumptions that I will not be considering here. The only thing I will do that simplifies things is that I'm only interested right now in the propagators. So I will only include terms that contribute to the quadratic action around Minkowski. And so collecting all the parts, basically this is the action that you end up with. So this is the kinetic term, and there's some arbitrary, well, unknown parameter here, which basically tells you the relevant coefficient. And this is 1 in general relativity. And you have these 2 derivative terms, 4 derivative, and 6 derivative terms. And these are basically suppressed by some scale m star. And these are the terms, and dot, dot, dot correspond to terms that are not, that do not contribute to the quadratic action. And so in the gravity sector, we have the usual tensor modes, but because we have a more less restricting symmetry, For example, we have a time reparametrization invariance that is time dependent only. So this is not really enough to reduce the number of degrees of freedom by 1. So we end up with an additional degree of freedom, which is the scalar graviton. And when you look at the dispersion relations, for example, for tensor modes, we have this nice expression. We have the usual second order part, and then it goes up to sixth order. So basically in the UV, the propagator is 1 over omega square minus k squared, k to the 6. For the scalar mode, you have also something like that. It's more subtle, it has some denominators, but if you look at the UV behavior, it actually also behaves like k to the 6.
Is this true for any choice of the parameter alpha and beta or whatever?
Well, as long as you, I mean, these beta 3 basically is just coming from. So basically, the tensor mode only sees this term, for example, and I think scalar mode sees all of them. But yeah, if for some reason you have a reason to set this to 0, you can at least at the classical level you can see that you don't have the sixth term. So the connection with GR is basically at low momenta, when your momentum is less than m star, these terms are basically suppressed, and you can recover GR when lambda is 1, this beta is 1, and alpha is 0. So now I will move on to the second section, and first let me do some let me do some theoretical considerations and to understand how these terms can behave. Like, I mean, the language is a little different than what Diego used. He was using basically the chronometric theory, and unfortunately, we also use alpha, beta, and lambda, which correspond to different things. But anyway, but the idea is the same. So basically, you want the scalar mode, which has a kinetic term that depends on lambda like this, to be positive, and you have two regions that you are allowed. One is less than 1/3, and the other is greater than lambda, greater than 1. And since you want to be connected to the GR regime, or at least approach there somehow, you wish to be in this part of the parameter space. And also, if you look at the infrared dispersion relations, which go like this, so you have these propagation speeds. Again, if you want to avoid these gradient type instabilities, this basically puts this type of bound, inequality between alpha and beta. One issue with this theory is that the two-time derivative terms at cubic order may actually dominate over the quadratic ones. So this is kind of a signal of strong coupling, and this is basically a breakdown of perturbative expansion, and the whole power counting arguments rely on the perturbativity. So then you are not sure whether this theory is still power counting and normalizable if you lose perturbativity. And Diego and collaborators have calculated the scale at which this strong coupling appears. If you assume that alpha and lambda minus 1, so basically the departure from their GR values, are of the same order, you can estimate the strong coupling scale, as Diego showed, as square root of alpha times m Planck. And also, this is a problem with the infrared theory. And so if the UV terms, the higher dimensional terms, come into play at lower energies than this scale, then actually this issue can be screened. I mean, the instability will be there, but you can never reach it, because you will go to the UV regime. And now what I really want is to get some bound on this parameter. For that, I need to understand what are the bounds on this alpha, which already was spoiled by Diego in the ending. The stringent constraints come from these ppm parameters alpha 1 and alpha 2, which measure the preferred frame effects. And if, again, you assume that the departure of these parameters from the GR values are of the same order, then you end up with this 10⁻⁷ type bound. And Diego also talked about the special case, which is, again, a different relation in this language, but you can basically have a larger bound to this. But assuming that the parameters are not tuned, so there are no cancellations and everything is of the same order, then you can basically estimate the upper bound on the strong coupling scale as 10 to the 16 GeV. And then, again, if you require that the theory is perturbative at all scales, which means that the UV terms, the higher dimensional terms, have a lower suppression scale, that basically puts an upper bound on this M star. So, okay, well, and we have an upper bound on M star, but we do not have much information from the gravity sector. We do not have too much constraints on M star. You can basically say that down to sub-millimeter scales, we know Newton's gravity is a good description, has been tested, so this can put a lower bound at 10 to the 2 eV or so. So this gives you an enormous window for M star. So things seem to be quite relaxed in the gravity sector, but if you want to introduce Lorentz violating operators in the matter sector, then things are more difficult. And again, as Diego said, I'm basically taking these numbers from the Coleman-Glashow paper, where you have different universality of propagation speeds constraints for different types of species pairs. And they're all of the order of 10 to the minus 20 and 10 to the minus 22. So they are really stringently constrained. And if you try to introduce some Lorentz violating operators in the matter sector, then even if they are suppressed by some Planck scale, the Lorentz violating effects at low energies will give you about 1%. About 1% difference in the propagation speeds of different species. And this was basically argued in this paper, and then a concrete example was introduced by Yengo, Russo, and Cerrone, where they considered two Lifshitz scalars, and they calculated one with correction to the propagation speeds and found the difference, basically. And although you can still make the delta C squared equals 0 as an attractive IR fixed point, they found that the flow is too slow. And it's basically logarithmic, and you have to do this type of tuning of a 1% quantity at the 10 to the minus 20 accuracy. So you have to have a very strong fine tuning. And these are about the dimension 4 operators. And even if you're somehow able to do some very strong tuning, or somehow there's some mechanism that suppresses the lowest order Lorentz violating operators, you might still get Lorentz violating operators that are generated in the matter sector at higher dimensions. So you might get, for example, a dispersion relation like this, where this M star M is this effective scale of Lorentz violation in this matter sector. And considering the synchrotron radiation constraints from the Crab nebula, Liberati, Maccione, and Thomas obtained a lower bound on this scale, which is at about 10 to the 16 GeV. And then the question is basically what would happen if the Lorentz violation had a universal scale in both matter and gravity sectors. And that would basically make this bound to be completely in conflict with the bound coming from theoretical considerations in order to avoid the strong coupling problem. Basically, you need the opposite of this. So this is just another example which basically tells that you need some mechanism to suppress the Lorentz violating operators in the matter sector. And even if you take the matter sector to be purely standard model, everything is Lorentz invariant at 3 level, you will still have through graviton loops Lorentz violation effects in the matter sector. And one idea was to impose some common symmetry between the two sectors, which somehow forbids the lowest dimensional Lorentz violating operators to be generated. And one idea in this paper was to consider supersymmetry. But there has been some developments in the last few years, and it seems like it's very difficult to get a supersymmetric Horava-like theory beyond the free case. So, and the way to so I think this is the most promising mechanism for suppressing the Lorentz violations in the matter sector, and by this I mean the paper by Pospello and Schenk. So, in their scenario, Lorentz violation in the gravity sector only. So you have a Horava theory in the gravity sector, and matter sector is completely Lorentz invariant. And in this case, the feedback of Lorentz violation from gravitational loops are basically depend on this ratio, Lorentz violating scale divided by the strength of gravitational coupling. And if you have some kind of hierarchy between M star and M Planck, the Lorentz violation in the matter sector can be under control. And what they did was they basically took some vector and the scalar field that are minimally coupled to the gravity and calculated one loop corrections, one graviton loop corrections to their propagation speed, and this is what they get. So from the loops that are contributed by the tensor and scalar parts, they get this M star square over M Planck squared kind of suppression. So this basically does what they wanted to do. But there's a problem here, which basically comes from the gauge mode loops. And there's a quadratic divergence. So this basically is signaling to a problem of Horava theory, which is actually the higher dimensional operators do not affect at all the vector sector. So it's, the propagator of the vector mode is exactly the same as in GR. It is completely blind to these higher Horava terms. And as a result, you end up with this big naturalness problem, basically. And they also suggested a resolution for this. And the suggestion was to add some new term, which is normally excluded because you're only including up to 6-dimensional operators. So if you look at this, this has 2 time derivatives and 2 spatial derivatives. But they found that actually this doesn't affect the tensor propagator at all. And the scalar propagator is modified, but its UV behavior is still like k to the 6. So on the other hand, this is affecting the vector prop mode. So instead of going 1 over k squared, the propagator goes like 1 over k to the 4th. And they found that this is actually sufficient to make the loop integral logarithmic. And in the end, this contribution from the vector part becomes, again, suppressed by lambda square over M Planck, where lambda was this scale. And assuming that these scales are of the same order and much less than M Planck, basically this shows that you can have the leaking of Lorentz violations to the matter sector can be suppressed. And if you try to make this number at around 10 to the minus 20s, you can estimate the M star, a bound on M star, which is about 10 to the 10 GeV, which is, well, in the middle range of the vast range we had before. On the other hand, there are some question marks with this whole mechanism. So basically they're using some term that seems to be beyond the whole counting arguments. And there are many terms they can add, but they only take one of them. There are other mixed derivative terms. So one needs to understand whether the other ones can, do they need to be tuned away, and also what happens to the scaling of the theory. I will answer this question last. So let me try to add all the possible terms which have 2 time and 2 spatial derivatives, and look at the propagators. Why are they not included, and do we have to do the tuning? So there are 3 possible terms which have 2 time and 2 spatial derivatives, and only one of them contributes the quadratic action around Minkowski. And this can be written in 4 independent forms like this. And this term, dikij, kjk, was the one that was used by Pospello and Schenk. And if you do a calculation of the vector action, you see that the new k to the 4 part is contributed by not only this term that they use, but also this gamma 2 term. So that's one information. The second information is that the tensor dispersion relation becomes this. Now these betas are the original Horava coefficients, and this gamma 2 is one of the new ones. So what you see here is if gamma 2 has a generic value, in the UV, this part is k squared, and you have a k squared here, so your dispersion relation, instead of being k to the 6, now is k to the 4. So you're basically decreasing the power of your propagator, tensor propagator. And a similar thing happens in the scalar dispersion relations. This is quite ugly, but this is the standard part, which depends only on the Horava coefficients. And the new part comes here with R2, P2, and P4, which depend on gammas in this way. And again, because of this P4 term, in the UV, this term goes like 1 over k squared. So again, the dispersion relation of the scalar field, scalar graviton in the UV goes like k to the 4, again for generic parameters. And what Pospelov and Sheng was doing was basically setting everything except for gamma 1 to 0. So this term was absent, and this setting was also killing P4, but keeping R2 and P2 non-zero. And you can actually do a less restricted tuning if you want to do the same thing. You can actually, instead of fixing 3 parameters, you can fix 2 parameters. And once you do this type of tuning, you can end up with tensor and scalar modes that have dispersion relations that are 6th order, but the vector mode has a modified dispersion relation. Okay, this is kind of a generalization of the tuning they had. And so it keeps the scalar tensor propagators the way we know, but improves the gauge mode loops issue. But this is a tuning that you do at linear order. So you don't really know whether it's radiatively stable beyond that. But even beyond this, the question I'm asking is whether this tuning is really necessary and what's wrong with the 4th order dispersion relation. So the main point is as follows. The 6th order dispersion relation that we think are necessary are based on a counting that was done where the kinetic term was dominated by this term. But here we have this type of term, which indeed, because you have an extra k squared term, at high momenta, this will be more dominant over this one. So you have to really revisit the counting. And we do this based on, again, a toy model of Lifshitz scalar. So we have the usual canonical kinetic term and this mixed derivative term with some gradient. But now for the moment, I'm keeping the anisotropic scaling arbitrary. So I have some arbitrary m. And choosing the normalization and fixing the units such that these two terms have the same dimensions, it turns out that you have to, in order to do the second thing, you have to have a relation m equals z minus 1. So in Horava theory, you didn't have this because you needed this term to be of the same dimension as this one. But now, because these two are dominant in the UV, you need to make these two to be of the same dimension. So this affects the relation between the gradient term at the time anisotropic scaling. And then you can look at the dimensions of the scalar, and from this you can find that the coupling constants for self-interactions have a positive dimension if this condition is satisfied. So, and we get the same result for when we included the derivative interaction. So the whole more detailed proof is in the paper. So let me rewrite this condition for d equals 3. So we're in d equals 3 plus 1 dimensions. So in the minimal case, which seems to be power counting renormalizable, z equals 2, and what is interesting is that m basically is 1, which means time and space now scale the same way. You have a relativistic scaling with up to 4th order gradient terms. However, the problem is you already have a mixed derivative term, and since time and space have the same dimensions, there's nothing that forbids you from adding a term such as phi double dot square. So if you're in this case, you will have basically a breaking of unitarity. And even though this is power counting renormalizable, it's very much like the stainless theory. It's relativistic scaling, power counting renormalizable, but you have basically a unitarity breaking terms. On the other hand, this doesn't have to be equal. So if you go to the next possible value for z equals 3, you add up to 6th order spatial derivative terms, and now your time basically has time derivatives that have 2 momentum dimensions. And actually, in fact, you can avoid having higher time derivatives in this case. If this is the UV dominant operator, then there's no way you can have a higher derivative operator like this to be present. And if you look at the dispersion relations in the UV, they're going like this. So it's 4th order in momentum is the omega. And in fact, this is exactly the case I showed you before. We had standard Horava theory, which was modified by adding these mixed derivative terms. And standard Horava theory had z equals 3 gradient terms. And we have the mixed derivative terms, and also the dispersion relation turned out to be 4th order. So this is exactly the case that we considered. And this looks like both power counting renormalizable and, well, unitary. And you can actually go ahead and add arbitrary mixed derivative terms, where I'm not sure if this is visible, but this is y, which is the power of the Laplacian. And as long as you add higher and higher gradient terms, you can still have power counting normalizability and unitarity. So this is a region plot where x-axis is this y exponent, and the y-axis is this m, which was the measuring the anisotropy between space and time, and it's related to z through z minus y, basically. And the darkest region is the combined allowed region, and the green dashed line corresponds to the power counting renormalizability condition. This red line corresponds to one of the unitarity conditions, which basically is powers of phi double dot. And this blue line corresponds to excluding powers of phi double dot combined with phi dot. Powers of phi dot. So these two comes from unitarity conditions, and this one comes from power counting renormalizability. And this green line itself is also excluded. So if you look at the Horava theory sits on this line, and you can see that you have to be beyond 3. This is for d equals 3 dimensions. And for the case that we considered, where you had 2 spatial derivatives and 2 time derivative mixed terms, this point is excluded. This basically corresponded to the relativistic scaling. So the next one that's available is here. So basically, you kind of have an infinite versions of extensions of Horava theory that seem to be possible. So now, let me conclude. There is not much constraints on the Lorentz violation scale of the Horava theory M star, and it allows you to have a very small M star over M Planck. And this type of scale hierarchy can prevent Lorentz violations to percolate into the matter sector. And the vector modes are blind to the Horava terms, and they lead to quadratic divergences. And a proposal was to include some extension with mixed derivatives. And the tuning that was used in the original paper of Pospello and Sheng was to keep the 6th order dispersion relations in the tensor and scalar modes, and only allowing modification to the gauge modes. It seems to work, but it's not clear whether this tuning is either stable or even necessary. And we found that once you add these mixed derivative terms, you need a different counting. And when you do the different counting, actually these 4th order dispersion relations can be compatible with the power counting renormalizability and unitarity. But the question is whether, using these new propagators, will the nice features of Pospello-Sheng mechanism still be valid or not? So that's one thing that needs to be done. So
that's where I stop.